All right, so let's start the Friday morning JKMRC Seminar series. So on behalf of the University of Queensland and the Sustainable Minerals Institute, I'd like to acknowledge the traditional owners and custodians of the lands on which we meet today. We pay our respect to their ancestors and their descendants who continue cultural and spiritual connections with country, and we recognize their valuable contribution to Australian and global society. So for today's seminar, it is my pleasure to welcome Professor Nadja Kunz. Yeah, good. Nadja holds degrees in chemical engineer and business management and a PhD from UQSMI. Prior to joining University of British Columbia in 2017, she was a postdoc at EWAG in Switzerland and consulted as water specialist for the International Finance Corporation. Nadja has operational corporate consulting experience within the mining sector and has worked on projects in Australia, Canada, Mongolia, Indonesia, Ethiopia, Chile, and Peru. Nadja has extensive leadership experience, currently co-leading the water stewardship theme for the Bradshaw Research Institute for Minerals and Metals, and play a leadership role within the Future Minerals Initiative, which aims to reimagine the future of mining. So today, Nadja will give us a talk titled Mitigating Mine Water and Waste Legacies Through Interdisciplinary Approaches. So let's give a warm welcome to Nadja.
Thanks very much for the introduction, Daniel, and for setting everything up today. And it's always a real pleasure to come back to UQSMI. And I spent a lot of memorable years here during my PhD and prior to that. So really appreciate everyone being here, and great to see some familiar faces as well. I know it's International Women's Day today as well, so I think there's quite a few folk that are busy with other engagements as well. So I just wanted to acknowledge the day that it is. And so today I'm going to be talking, as I said, around just some of the research my team's been doing, really looking at how we delve into addressing legacy issues around water and waste. And my position at UBC is a really fantastic one for me, because I sit jointly between a UBC School of Public Policy and Global Affairs and a mining engineering school. And so for those who know me and my work, you'll appreciate that I really am very passionate about interdisciplinary work. I think that it is truly the only way we're going to address some of the biggest challenges the industry faces. And so that's what drives me in the work that I do, and I hope you'll see coming through from the presentation I have for you today. So as Daniel said, we are also here today on the lands of the Yugara and Turrbal people here in Brisbane. And I think land acknowledgements are really important. Sorry, this seems to not be working, so I'm just going to pop over here. I don't know why it's not. Tested it a minute ago. So a lot of the research that was conducted was at the beautiful UBC Vancouver campus, which sits on the traditional territories of the Musqueam Nation. And as I said, these land acknowledgements are really important for mining, because a lot of the mining legacies that we create are often on the lands of traditional people. And as you'll see from some of the context that I'm going to set around what really drove me to take up this question of tailings risks was really coming from a lot of what was happening in BC or just prior to my arrival in Vancouver. So in 2014, there was a major tailings breach at the Mount Polly tailings dam. So that I joined UBC in 2017. This happened several years prior to that. But that breach, thankfully, it didn't kill anybody, but it did lead to significant effects on local water systems. And that had very real concerns for a lot of First Nations communities in the province. So the tailings breach happened at Mount Polly, and some of the debris actually flowed through into Quesnel Lake, which is quite an important lake for a number of recreational reasons, but also has traditional significance for local people in the area. And following that Mount Polly tailings breach, some really interesting things happened. One of them was that Imperial Metals, who owned the Mount Polly mine, were trying to develop the Red Chris mine up in the Tahltan Nation in northern BC, significant distance away, but owned by the same company. And they had significant challenges, around that mine. There was blockades led by some First Nation elders, actually women, a group of women elders up in the Tahltan Nation, who were blockading the mine. And I think it was closed, it led to some significant delays for that project. Further to that, there was also another project that Imperial Metals was trying to develop in another region, and the exploration for that was also compromised because of these very real concerns from First Nations in the province around the significance of tailings breaches. There was also some really interesting work done by the BC First Nations Energy and Mining Council following Mount Polly, where they were looking at where all of the tailings dams in British Columbia were located and how they intersected with watersheds where there were First Nations communities. And you know, just to highlight some of the things that were in that report, you know, really highlighting a lot of basically just looking at whether a tailings dam was upstream of a watershed that was in a First Nation region, and also basically just trying to understand what those impacts might be, particularly around salmon and other cultural reasons that were important for those First Nations. But really, this work is just to kind of highlight the context around this being a very, very significant issue in the BC context, and that's really kind of what drove me to get very interested in this question. And then several years later, many of you will know the high-profile and very unfortunate tailings dam disaster that happened in Brazil with the Brumadinho tailings failure, which resulted in hundreds of deaths and had widespread environmental damage as well. But those life losses were significant in this case. And following these events and many others that have unfortunately happened globally, this really led to a significant investor action around trying to bring more attention to tailings dams as an area of priority. But from a research perspective, it was also a really exciting time because for the first time we had an incredible tailings portal developed following through from that Church of England and an investor-led initiative to make disclosures of tailings dams public. We actually had, for the first time, around estimated about 20% of global tailings facilities, able to be summarized in a useful way with lots of information about those facilities and their consequence classification. So that was the first time that kind of data was publicly available. So we started to think, what within my research team, how can we make better use of this data set? At the time when we started our work, this beautiful tailings portal on the right-hand side didn't exist. So it was still quite, the information around tailings disclosures was still published on various different websites and hadn't been compiled. It's now quite well compiled and really useful with a very user-friendly interface. But nonetheless, we were interested in, could we use this data set to do some really interesting research? So a couple of things emerged from me from watching these tailings failures and someone being very passionate about water-related issues. The two things that I became very interested in are, number one, what tools could we use to improve quantification and response to these kind of regional level portfolio risks posed by tailings dams? Acknowledging that for investors and also for First Nations and regulators, they're not necessarily interested in only understanding impacts at one facility. They want to have a portfolio level understanding of what their risk exposure is and how it may affect their interests. The second thing we were interested in, or that emerged for me, was where are the levers that we can use to strengthen the economic business case to really shift the dial and avoid these kinds of tragedies? So how can we make better business cases for more technological innovation? So I teamed up with some wonderful collaborators who I've had the privilege of working with over the last several years. The first one is Sally Innes, who just defended her PhD a couple of weeks ago. Benjamin Cox, who is leading the Bradshaw Research Initiative of Mining's educational program, but also doing his PhD with Professor John Steen and I. And John, who some of you may remember, he used to be a professor in the business school at UQ and then moved over to UBC. And he's also been part of this work. He leads the Bradshaw Research Initiative in mining at the moment. So the first research question I'm going to run through is what kind of tools can we use to better understand these regional scale risks? And so a lot of this work was led by Sally Innes. And what we did was we recognizing this data set that was available through that global tailings database, we teamed up with some collaborators from the School of Earth Sciences at UBC. And they had been doing research on tailings dams, but they'd also been doing a lot of research looking at lahar flows, so looking at other kinds of natural hazards. And what we were able to do in this work was to recalibrate a model that had been developed for understanding lahar flows, developed through the USGS, GIS-based model, which looks at a number of characteristics around the mobility and the volume to predict how far a lahar would flow in the case of a failure. We recalibrated that for the purposes of looking at tailings flow. So it's a coarse model. It's not going to be anywhere near as accurate as doing a site level numerical model for tailings flows, but for our purposes, we thought it was a great tool because you could actually very quickly, with some quite simple inputs in terms of the release volume or the volume of tailings waste that was in the dam, you could then predict how far it would go based on the local geology and around the area. And so we were able to calibrate this using historical tailings dam failure events that our team had been developing for other projects, and to recalibrate this model for use in our purposes. And so this is just an example on the bottom there. The left-hand side figure shows the extent of the tailings dam failure at Brumadillo, and then the right-hand figure there is what our model predicted, how far our model predicted that would flow. There are some limitations to what the model is able to predict. For example, if it intersects with a waterway, it doesn't model the flow through the water body, but we think there's opportunities to maybe couple these models with other models where you can look at sediment flow in waterways. But anyway, that's kind of the purpose of what we were able to do. And the nice thing about it is it runs quickly and you can run it over many facilities quite quickly. So we applied this model in this first paper to 46 Canadian facilities. We were interested in understanding regional scale risk posed by tailings facilities. And this figure here is showing on the x-axis the modeled inundation area. So we found for those 46 TSFs that we looked at, they would flow between 2.2 square kilometres and 4.8 square kilometres. And it depends on your assumption around how much of that volume will actually leave the facility. So probably not 100% will leave the facility. We have a range on low and high release volumes. The colours in this are actually the self-reported consequence classifications from the respondents to the tailings disclosure survey. And what we found was when we were comparing British Columbia with other parts of Canada, in general, there were quite a high number of high to extreme consequence classifications and also modelled inundation areas that were above the Canadian average. So what we've done since publishing that paper, which was really the development and proof of concept of that model, is that we've now got a paper that we're currently revising for a journal where we've looked at applying this model to 5 different case study countries. We've modelled, in this case, 248 facilities. There are some limits to what facilities we're able to model, and I'm happy to talk to that a little bit in the questions if that's of interest, but we do have a filter to decide on which facilities are best suited to this particular kind of model. But what we did, and as you can see from this figure here, is basically using the tailings data from the 5 case study countries that we focused on. We use the LaharZ-T model, we're calling it. So LaharZ-T is the one for lahars, and we've called it LaharZ-T for tailings. We generate information about the tailings location and information. We have the digital elevation model, which is basically what will drive where that flow will go. And then the inundation polygons are what we generate through LaharZ-T. We then combine that with proxy indicators for different environmental and social consequences. So in this work, we were looking at overlap with human population distribution, river and lakes, and protected areas. And these are obviously potential failures. We're not suggesting that any of these dams have or necessarily will fail. We're not looking at likelihood. We're just looking at if they failed, where would they go and what kind of social and environmental consequences might that have. And so that's kind of the broad methodology around how we put these pieces together. So essentially we're overlaying the LaharZ-T model with these different proxy indicators of different kinds of hazards that we're interested in. And so this is a summary table that shows the frequency of any degree of impact with those 3 proxy indicators. So and it's important to note here that particularly it looks like the protected and conserved areas has a reasonably low frequency, but you have to recognize that there's actually less conserved areas than what there are urban populations, for example. So it hasn't been scaled relative to how much protected area there is. So really any kind of intersection with protected and conserved areas is very concerning, even though it looks reasonably low in this situation. But very interesting things start to emerge when you look at these tables, when you're comparing different countries and the kind of risks that they face. So in the case of Canada, for example, it was unsurprising to me to find that there was a very high intersection with water bodies. So the tailings dams, if they were to fail, there's lots of natural lakes in Canada, and more so than in Australia, for example, and quite a high probability of intersect there. And likewise with Brazil, water bodies was a frequent impact that occurred. And in the case of human population, I have to say I was a little bit surprised that Australia's intersection with human population was as high as what we found. Canada certainly has a lot of mines in very low densely populated areas, so the frequency was quite low in the Canadian case. But certainly the other interesting one I think is South Africa, where we do have lots of facilities that are quite close to communities, and so a high probability of intersection there. So I think it's, in some ways the results are not super surprising if you think about the characteristics of the different countries we were looking at, but I still think it's quite fascinating to look at where there are differences in things we might have expected to find but didn't find, and also just to generally get a bit more high resolution modelling around where those impacts may be. And so this is another interesting thing that we looked at. We didn't, due to the size of the data set that we were actually able to model, it was very difficult to get statistical relationships with statistical confidence. This is one where we did manage to find statistical significance. So we were looking at the construction type, whether it was an upstream dam or a non-upstream dam. And this is just comparing South Africa and Canada, which were the two where we found statistical significance. So I guess firstly, there are more upstream facilities than non-upstream in the South African case, and the opposite is true in Canada. But what we did find is that South Africa is particularly at risk of having upstream facilities that are located with the potential intersect with human population. So that's really quite concerning when we think about the potential for failure. So, and in Canada, the non-upstream facilities, it was more common to have non-upstream facilities in the proximity of human populations. So I now want to move to the second research question we were looking at, which is around what levers can we use to strengthen economic business cases for technology adoption. And the context for this is really that within the mining sector, I think most of you would probably agree that there are many great technologies that exist for improving water conservation, improving tailings management, but they're not always adopted to the potential they could be. And so I was interested in, how do we shift the dial around getting better technology adoption? The work we did in this project was sponsored by FL Schmidt, a technology provider, and MyTax, which is a program that provides matching funds for industry-sponsored research projects. And so we were mainly interested in two key things, and we published two papers in this work. The first one was around quantifying the actual cost of disposing wet tailings. So as with many other environmental issues actually the mining industry has, tailings is an area that often cuts across many different parts of the business. And when we think about where the challenges are of getting accurate costing around how much does it really cost to dispose of wet tailings, we found from our work that those costs accrue across many different parts of the business, and a lot of that is not compiled into one single cost metric. So our goal here was to really get a fulsome estimate of how much it costs to dispose of wet tailings. And that's really important, because if you're going to try and encourage the adoption of technologies that may, for example, extend the lifetime of a tailings facility by depositing waste at a lower percentage solids, you want to be able to say, what difference does that make economically to the business? So that was the first paper we did, was around looking at 43101 reports from tailings, from mining companies, which published lots of information that we were able to use in our model. And then also the second paper was around developing a financial model to look at what the business case was for investing in different equipment choices. And so we've got a public model that's fully publicly available with the paper, where you can actually use that to researchers can use it, but also operators or consultants to look at making a business case around technologies, depending on a lot of the different variables that you have at the particular site you're interested in. And so I guess, you know, when we think about the mining life cycle, the best point at which to make changes in technology decisions is always going to be in your pre-feasibility phase, but there's always an incentive to go with kind of the status quo. So we were interested in, you know, how do you make business cases early to adopt better decision making around technology adoption? So the first paper that we have is around the actual costs of wet tailings. And as I said, you know, our work found that the actual cost of tailings storage facilities is undervalued in a lot of preliminary economic assessments. And as a result, we tend to default towards using traditional wet tailings disposal for a lot of projects when maybe there could be an economic case to have a shift. Current financial reporting also tends to underestimate the value of dewatered tailings disposal options. And so our unified costing metric is really designed to be an early stage benchmark for encouraging, but thinking about the adoption of drier disposal methods. So the financial model, as I said, is helpful for decision making on equipment choice and can be used by everybody because it's open to the public. So this is kind of the different types of costs that we were looking at when we were thinking about how much does it actually cost to dispose for each cubic meter of tailings. So we looked at capital costs, operating costs, some of the closure costs, and also costs around dam lifts. What we didn't do in this work is we didn't account for the potential risk of failure or the true closure costs around closing tailings. So as I'll show in a moment, and as you can probably see from the table on the right, you know, I guess the ultimate conclusion of our work really was that oh, sorry, that's actually highlighted the wrong thing. It should be this one here, that we quantified the total cost of disposing wet tailings per dry metric ton being around 2.29 US dollars. And so that already is, from the experience in our team, a higher cost than what most preliminary economic assessments would assume it to be. And if you accounted for the closure costs that we didn't consider, the economic business case would only be stronger. So really this is around trying to illustrate that there is a lot of economic reasons for investing in technology. It is worth acknowledging, we did develop this model, or this application is based on Tech's QB2 project. So those costs depend on how much the price of, they will depend on a lot of local factors as well. And there may be differences depending on the context also. But that's, I think, an opportunity for future work, is to look at those unaccounted for closure costs and try and incorporate those also into our economic model. The second model that we looked at was also tested at a Chilean mine. It's a hypothetical Chilean mine. But what we did here was we looked at three kinds of technologies that could potentially reduce basically reduce the moisture content in tailings and ultimately, as a result, reduce kind of the hazards around wet tailings disposal. The open source model that we developed here compared optimized thickeners, hydrocyclones, and filtered tailings. So they were filter presses. They were the three technologies we looked at. So for those of you that like flowcharts, you know, this is kind of the modeled equipment packages that we use. So we looked at, you know, this is kind of the traditional most traditional wet tailings disposal. We looked at having an optimized thickener, a hydrocyclone, and then thickener and filter press going to dry stack. And what we found from this work was that the payback period from having an optimized thickener was only around 7 days. And I remember when I first started my first job as a graduate chemical engineer, I was looking at optimizing thickeners. So it was kind of disappointing for me that we haven't optimized thickeners yet, because it's such an easy win. So we also looked at hydrocyclones, filter presses. And when you compare, in the case of Chile, you're paying $3.75 per cubic meter of desalinated water that you're bringing for your operation. So all of the equipment packages that we looked at delivered water at a cost that was lower than what you would pay if you were sourcing water from desal. So very strong economic case for any kind of technology that's going to reduce water consumption at site. So that was the main conclusion of that work. And I'm very interested in future work to kind of expand this model to look at other kinds of, sorry, just checking that everyone can hear me online. Yeah, all good. Just checking it wasn't an issue with sound. So in other situations, you may need to make different economic cases depending on how much water costs and other drivers that may influence technology choice. But certainly for Chilean mines in water scarce areas where they're desalinating seawater and pumping it significant distances, it makes sense to optimize water conservation at all opportunities. So finally, I'm going to turn quite quickly now to future research directions and just touch on a couple of ways that I want to bring this work forward. So the first of them is that I am interested to apply LAHARS-ET to even more facilities globally. And also I find that the amount of information that's disclosed around tailings facilities is growing all the time. So I think in the future, we're going to have even more data available that we can use to do interesting research in understanding tailings risk. So what I'd like to do is take some of those new data sets that are coming online and increase disclosure to have further application of LAHARS-ET. So again, kind of following the same type of methodology that I described in our earlier work, but also starting to combine different kinds of potential consequences. So I'm really interested, for example, in whether we find that tailings facilities are more or less likely to intersect with communities of lower socioeconomic advantage or disadvantage. I think there could be reasons for both. That's one area that I'm particularly interested to explore further, but ultimately kind of repeating the similar analysis to what we did in Sally's earlier work, but at more facilities so we can start to better understand some of these local contexts and how they influence risk. The other thing I'm interested in is trying to look at how mitigation strategies might reduce that potential consequence. So for example, I've talked about some of the technologies we can use to make better economic cases around moving towards drier tailings. But there are also a lot of nature-based solutions that might reduce how far a tailings disaster might flow in the case of a failure. So it would be really cool if we could adapt this model to look at some of those mitigation strategies and be able to say, if we adopted tailings thickeners at all sites, what difference would that make for consequence profiles? There's still some there's certain adaptations we have to make to the model that we don't have right now around tailings and mobility, but that's an area I'd be really interested to explore. And also if we're having some of these nature-based kind of solutions that can ultimately change what that digital elevation model looks like, what the final landform looks like, and that then also has an effect on how far we model potential inundation zones. The other thing I'd love to do is to combine, so this work with Sally is really just focused on consequence. So we're just looking at potential failures and potential consequences. There's nothing about likelihood. One of the key risks that is coming and is actually already there for a number of facilities in Canada is around climate change and what that means for legacy issues around mine waste. So I'm just going to talk quickly about some of the parallel work that my team's also been doing on climate change risk in Canada. And I'd love to, in future work, try and bring these two pieces together. So in a separate project that we have been doing, which was partly funded by Vale, we had a collaboration with them for 3 years on a major project looking at water and climate risks. But this is just one small part of that project that I'm going to talk about. And basically what we did was I hired a postdoc who is a hydrologist, and Wahid Palash. So he was leading a lot of this work together with the other collaborators in our team. And what we did was we developed a climate risk assessment for mining watersheds across Canada. So this is a map that shows all of the principal mineral and mining areas across Canada and shows which watershed they're in. So what Palash did was basically went out and looked at climate projections for the country, downscaled them to each of those regions, and then was able to develop indicators around how the changes in hydrology would result under potential climate change scenarios. I should say these are the indicators that we looked at. We were very interested in how climate change would intensify water-related risks. So a lot of the things we looked at are about, they're about kind of hydrological variables. So things like intensity duration, frequency, what kind of short-term rainfall events are you going to have, the total precipitation, mean temperature, drought indices, and snow depth. Snow depth is really important for Canada, not so much for Australia, but in the case of areas that have significant amounts of snow, if you've got melting permafrost up north, for example, that's been identified as a major hazard for Canadian mines, but also if we're having changes in snow depth or increased snow melt, that has changes in the hydrological cycle around potentially having different flows of water at different times of the year. So earlier snow melt than what you might have had before, and also potentially larger flows of water as well. So quite a significant variable in the Canadian context. So I'm just going to highlight a few of the maps here, and this is work that is currently under review, so we haven't published it yet, but again, hopefully it'll be out really soon. But I'm just going to highlight a few things that I think are indicators that are conceptually quite simple to follow, and that highlight some of the points I want to make. So we looked at changes in annual mean temperature, and basically these are, for those who are not so familiar with climate models, basically they have two different projection scenarios. So there's RCP 4.5 and RCP 8.5, which relate to different kinds of assumptions around how our emissions will change in future. And then we have three projection years, so the 2020s, the 2050s, and the 2080s. And what's interesting for me is this scale here. So basically everything is positive. So everywhere across the country is projected to have increases in annual mean temperature. And obviously we get differences depending on exactly where we are in the country. And as you can see, with the more extreme scenario under high emissions and furthest into the future, there's projections of the greatest increases in annual mean temperature. We also looked at increases in annual precipitation. And again, I say increases because in all cases, the scale here is positive. So all of the watersheds that we looked at are projected to have increases in annual precipitation, and also some slight more variability, I guess, in terms of trends here that you can see across the country, but certainly everywhere is tending to get wetter. We're also seeing decreases in snow depth across all of the scenarios we looked at. So this is percentage change, but it's all showing decreases. And these are the different provinces where we were looking at different watersheds. Again, the most extreme scenario furthest into the future showing quite significant decreases in snow depth, and that has very significant implications in relation to water and tailings. So just to kind of sum up some of the things that, conceptually could occur as a result of those shifts in the climate, certainly increased risks of overtopping or TSF failure with subsequent potential impacts downstream, collection ponds and containment structures being overwhelmed if they're not managed better, and water quantity and quality management challenges, and certainly that decreased snow melt and also melting permafrost, which we didn't model but has been done in other work, potentially contributing to increased stream flow in some regions. And ultimately for me, this really begs the question of what does this mean for closure? Because a lot of these projections are, we're talking 2080s and beyond. It may be beyond the operating life of some mines, but certainly the legacy issues that will leave are really concerning to me and quite significant that attention is given. Thankfully, there has been a lot of action on climate change in Canada. The Mining Association of Canada did produce a guide for climate change adaptation for the mining sector to encourage the adoption of climate projections for infrastructure design, and really trying to encourage that as a priority. And that's also been the case from a lot of regulations as well. There's now an expectation in environmental impact assessments, for example, that climate change will be considered in infrastructure. But one of the challenges is that it's not there's not a lot of detail around what that consideration should look like. So there's still some work to be done there. But certainly there are increased media interest as well, and reports on what climate change could mean for Canadian mines moving forward and some of the challenges thereof. So final slide, I just wanted to kind of reflect on some things that I've been thinking a lot about. So I'm here on sabbatical from UBC at the moment, and basically, been spending a lot of time thinking about what's different between Australia and Canada in relation to these kind of three areas that I've talked about today. So the first thing is that, context is, well, I suppose the overwhelming message here is that context matters. But certainly when we look at modelling potential TSF consequences, in the Australian example, we found, higher frequency of impact to human populations in comparison with water bodies or protected areas. And in Canada, we found, water bodies are really the greatest risk in relation to potential intersect with human populations or protected areas. So, context differences in terms of that water body impact being quite significant for Canada. Also, I mean, Canada, like Chile, is a water scarce region. The economic business case for investing in technology, in many cases might be driven by the cost of water access or it's kind of easier to make a case for saving water if you're in a water scarce area. Thankfully, Australia doesn't have to transport distances as far as many Chilean mines do. So, we haven't modelled that in terms of Australian mines, but generally business cases around water savings make sense. In Canada, it's more hard to make technology arguments on the basis of water savings because we're generally in much more water abundant areas. And so the justification for investing in tailings, I think, is probably going to be much more around, potential reduction of legacy around dams in the future. And also some of the recent work I've been doing, I've been looking at climate change projections. Queensland government actually has a great website that they've just updated, which shows some of the future climate projections for Queensland. And when you have a look at mining regions, I mean, across Queensland, there's a lot of differences in terms of how precipitation may shift, for example. But for a lot of the coal mining regions in particular, generally they're going to become drier and warmer, which means more evaporation, less rainfall. So the opposite is kind of true in Canada. You're actually dealing with a much wetter environment. So just kind of interesting when we think, obviously these are very general trends between Australia and Canada, but certainly that local context is really important for all of the things that I've talked about today. And I do see some quite distinct and interesting differences when we think about comparing Australia and Canada for the purposes of water optimization and tailings management. All right, so I'm going to stop there. Thank you all very much for your attention, and thanks to those who've joined online. Really appreciate you making time to listen, and yeah, really happy to continue the conversation. Are there any questions?
All right, thank you very much, Nadja. It was a very interesting presentation. Is there any questions in the audience? I have one, actually. So in Brazil, you have the Brumadinho tragedy was terrible there. And you show a lot like how important it is to look if the TSF is going to be downstream or upstream, like in relation to population density and everything else. Do you see after those tragedies a change in the government policies to take more care of this, or is it just being something that the mines are doing themselves? What's your perspective on this after this? I think it was one of the biggest tragedies that we have so far.
I mean, you might be probably more knowledgeable of some of the Brazilian regulatory change. I understand there was a move to avoid upstream construction methods. So I know some countries have moved towards that. I believe in Chile, they already have banned upstream for some time. So there certainly are regulatory reasons that have resulted in shifts around construction type. Yeah, I mean, in Canada, we do have upstream construction. There are also, in British Columbia in particular, they actually also have tailings dams, which are just deposited into lakes. So they're actually natural water bodies that are used partly for acid rock generation potential. They cover the tailings in natural lakes, which has its own challenges and problems, but it does reduce the chances of a downstream flow in the case of a failure because it's already in a lake, so it's not really going to go anywhere. So I think there's a lot of, it's a very long way of saying there's a lot of different drivers around construction decision and type. Yeah, I think there's pressures on on multiple levels, probably the industry is also moving towards, its own decision making around construction type. But I do find differences in countries around the policies on that. I mean, upstream construction, and I'm not an expert in tailings dam construction, but I do understand it's often well, there's different drivers of economics, but it can be an economically method of construction depending on the context.
Yeah, thank you. And do you see yourself, for example, in terms of legacy of those old tailing dams? Do you see like the government or any regulatory organization doing some work to check them out, and at least in Canada or Australia?
Yeah, I mean, I know there's been a lot of work on looking at reprocessing and repurposing, and I can see Anita's in the audience here. I know her team's been doing a lot of great work on looking at tailings, repurposing and reprocessing. I think it's great particularly if there's critical minerals in some of these facilities that could be reprocessed to tailings. The ore grades might actually look quite good in some tailings relative to fresh or greenfields mines, depending on the facility. But I think there's definitely a need to do more work on looking at that as a possible solution. But I'd also like to see us building dams today in ways that are going to be the best for the future, because there's a lot of factors to consider when we look at reprocessing of a tailings dam. There's still risks associated with that. And I know there was actually a tailings failure at a diamond mine in South Africa that was actually a reprocessing facility. I think, there's a lot of reasons probably for that failure, but it does highlight that any reprocessing really does need to be done with utmost attention and caution as well. Yeah. I can see some questions in the chat. I don't know if I should.
So I can read one. It's from Andy Fargin. So do you think dry stack tailing facility will be effective at the tropical region? Indonesia, for example, that has 4,000 millimeters rainfall per year.
It's a good question. I would love to probably defer to people that are a bit more expert in some of the limitations of dry stack or construction method, depending on local context. But I guess I think it's definitely worthy of looking into. I can see that he mentioned Indonesia. Obviously the rainfall there is significant in that region he's talking about. So yeah, I mean, I guess wet tailings disposal with high rain is going to be have its own challenges. So I think there's probably more work to be done, or others probably are able to comment a bit better on whether it will be effective at different in different rainfall environments. But to my knowledge, I don't think there's a limit to that being a constraint. It is more common to see dry stack at there's more of I've seen more discussion about dry stack use in water scarce environments, because the economic business case is kind of easier to make, because the case is being made around water access and water cost. But I think there's a very strong case to be made in situations that may be water abundant, where being able to have more consolidated tailings might actually be advantageous for other reasons around disposal and closure. All right, so there's some other, quite a few questions actually. You can take your pick, Daniel.
So Michael is interested to hear if connections with government, regional and urban planning have looked at to consider future planning. So how's the future planning are kind of holding on around like TSFs or something?
Yeah, we've had some connections. I guess the main connection that my team's had with government has been through a unit that's responsible, like the Ministry for Low Carbon and Energy Innovation. They have an auditing unit. We've been really interested in whether they might be able to use some of the models we've developed to look at auditing closed facilities and where the highest priorities might be, because a lot of in government auditing functions, there's a huge number of closed facilities and limited government capacity to go out to every facility on a very regular basis. So obviously they want to be able to prioritise facilities that are at highest risk by some definition. And so we have had some conversations around that, but it's more been in the case of auditing closed or closed facilities rather than new developments and urban planning. So I think it's a really great suggestion. I'd love to think more about that and you know, potentially connect with anyone that is in that space that might be on the line.
Thanks, Nadja. That was really interesting. With the climate modelling that you've done for Canada, it may not be as applicable for Canada, but I was wondering, as part of that, do you look at the intensity or predicted intensity of weather events rather than just the baseline sort of increase in rainfall, et cetera? Because that's mainly what the driver for these catastrophic events is.
Absolutely. Yeah, no, it's a great point. I mean, I just wanted to highlight a few of the, you know, a few of the trends that we were seeing, but definitely the work has looked at like intensity, duration, the frequency curves, which is kind of from a hydrological perspective, one of the key variables that infrastructure is designed around, which is kind of how much rainfall flows in short-term periods. So we did have a look at that as well. I know there's, overall, I guess there are expected to be kind of more intense events that are likely to create challenges. So I'm very happy to talk more about that and direct you to some of the work. But for sure, it's yeah, when we think about climate change, it's actually really important that we don't just look at averages. It's actually exactly as you say, it's those short-term one-off events, and particularly in the case of tailings failures that are really important. So yeah, thanks for that comment.
Nadia, can you go back to one of your very early slides, which is the pictorial comparison one of a model projection? Let's go back.
Was it in the tailings one? This
yeah, no, keep going. Way back.
Oh, here?
No. There.
Okay.
Now, exactly what is that again?
You know, what is this?
What your two pickies on the bottom right?
Oh, right. Yeah, so this one, it's basically empirical and modelled.
Yeah, I realise that, but exactly where is it?
So I believe it's this, I think it's this direction. So I think the tailings, I'm trying to actually remember, I think the tailings facility failure was there and then it flowed this way, or it could have been vice versa. Actually, yeah, it must be that way. But we looked at like, so our model kind of, we have to make a number of assumptions with the failure.
Hang on, that's real data?
Yeah, this is the real, that's the real failure. So
in Brazil?
In Brazil, that's
okay.
Right. Yeah, and that's what our model was predicted to do. So we had, I can't remember off the top of my head how many historical failures, but the group that we worked at, I mean, we connected initially with the group at UBC in Earth and Ocean Sciences, mainly Scott McDougall, but he had collaborators at Queen's University and Waterloo who they were involved in a much larger project looking at tailings facilities and failures. And as part of their project, they actually had data around historical failures. So we had a number of their historical failures that we used to calibrate our model and validate it. And then we used that model, which I think off the top of my head, I think it was around 20 or 30 historical failures that we used to calibrate the model. And then we used that model to simulate what potential failures would be for the data set that we had, which was 250.
So what you really got is a design tool, isn't it? I mean, have you got anybody interested, somebody planning a brand spanking new mine and looking at the location and so on of tailings dams, and then overlaying that on the local topography and so on? That would surely be a wonderful design tool to look at. Is that being used in that way?
So I suppose you know, I think this model is excellent for running many facilities at a moderate scale of resolution. If you wanted to just model one facility and understand what its flow would look like, you would use a different model. So what I mean is there's better, you would build a numerical model that was much more accurate than ours, because our model is only has a simple. So maybe. Yeah, I mean it does, but it performs very well in these kind of valley kinds of failures. There's certain situations. So for example, we called it the spikiness factor in the paper. If it's a very flat landscape, it's a bit harder to, and you've got to make a certain number of assumptions as well around the initiation point of which way the tailings will flow. And so we did that based on elevation. So we would assume that it would breach at the lower elevation. And, you know, we kind of, it was actually for each facility, you have to make some assumptions around that. So yeah, so it's a great point, Don. And I should think more about it, because maybe I'm, maybe I'm responding too quickly, but I would be very interested in how it could be used as a design tool. But I just caution that particularly our colleagues in Earth and Ocean Sciences have said, you know, it's not as accurate as what other models would be when you're doing site inundation models that consultants would usually build for those facilities. So yeah, I think it's a very useful tool for. It could actually be very helpful for companies if they have a large number of sites and they want to understand overall exposure across facilities. Also very useful for policymakers that want to know, how, what are the kinds of hazards that we face in our portfolio, or for, like I said, for auditing purposes, like where are the facilities that are likely to potentially intersect with, areas we don't want them to if they fail. And then also for, like for First Nations communities, I haven't gone back to engage with First Nations, but I think they could be interested, and investors, I think for sure. That was actually the audience we initially developed the model for, because we went out, Sally did qualitative interviews with investors after the tailings database came out, and basically said, how are you planning to use the database? And the answer we got was, we don't know. We don't know how to use it. And so we thought, well, can we build a model that will help you understand portfolio level risk? And this is kind of the model we developed as a result of that. Yeah, so long answer, Don, but happy to follow up more. You might be... I think you're selling yourself. I appreciate that. Happy to, yeah, definitely happy to explore that more, because there might be opportunities I haven't thought of for it. It's a good early tool, I think, for early decision making around design potentially.
Right. So there's an online questions from Neil. He says he makes some comments, and yeah, and like so one of the main things that he kind of highlights is basically like when you're talking about like hazards and something from TSF, shouldn't we also take into account like the rheological properties, like from like geological perspective? That I think would be, at least I'm a geologist, so for me it'd be very interesting. Like, should these parameters be accounted for?
Yeah, I mean, I guess we do have an assumption in there around the mobility coefficient, and that has been I guess one of the variables that we calibrated to within the model. But for sure, there's I think it would be great to further refine the model to be able to look a lot more at a lot of those properties. Right now, it does, like, it's true, it's a limitation of the work. It's always hard to have a model that does everything in the time. Like I said, the advantage of this is it just runs quickly, really. But yeah, I think it's a great area for future work, but something we haven't done yet. And I mean, when we present the results, we also do take care to not, I mean, this one is just a historical failure. It's, it's a validation of the model, but we have taken care in our results to present trends at, at regional levels rather than doing site by site comparison, because we know that at a site level, we may not be predicting exactly what's going to happen for a lot of the limitations that Neil's mentioning there. Yeah.
Makes sense. Yeah. Any other questions? All right. Just two more questions. I'll give.
That just got me thinking, would there be scope? Tailings are obviously a mixed bag of materials, lots of different minerals in there, but I mean, do different minerals behave differently? Like, are you more likely to end up with sulfides ending up in a certain part of a flow, or potential acid forming minerals, or minerals that contain toxic metals or whatever, versus where the silicates end up, for example, or the oxides? Do you think there's some value in looking at modeling that sort of characteristic from a more kind of complex perspective?
Yeah, I mean, I'd love to do that. I definitely agree. I think it would be a worthy area of future work. Our assumptions around that are very simplistic. I think even my understanding of what research has been done on tailings mobility and flow is that there's a need for much more research, because we actually don't I mean, I remember that was one of the first questions we asked our colleagues in earth sciences, like what research exists around how far tailings will flow? And the answer we got was, you know, it's limited. So I think there's a need for a lot more of that for sure, but we haven't incorporated it into the model yet. It's definitely an area for future work. Yeah.
Thank you. I want to defend your position on mobility coefficients. And while I absolutely understand the requirements for knowing what the rheology is and how to model it, rheology is something that defies modeling, because specifically for complex mineral slurries. We need to actually know what the heck the rheology is and have the ability to measure it before we can start implementing into models, all of those things that we currently haven't got. So I think you're okay.
Thank you. That's encouraging. Well, it'll be great to do, you know, when the work, when the research allows us to, it would be a great addition. But yeah, it's definitely beyond scope at the moment for the reasons you mentioned. Yeah.
Hey, thank you for your presentation. I have a question regarding the flow sheets that you show for dried tailings disposal.
Yeah.
So you mentioned optimize thickener. So that is related with paste thickeners, or you are aware that manufacturers are working in some new technologies or?
Yeah, it's basically just a process controlled thickener. So it's not a sophisticated technology choice. It was really just, you've already got a thickener and now you're optimizing its operation from a process control perspective. So that
any in particular? So normal PID controller, MPC.
I mean, I think I'm trying to remember where we got the data, because there is a lot of data that went into the model. I think we just made, it is an open source model, so you can go have a look at it, but we weren't distinguishing a particular technology choice. It was really just, you know, how efficient is the thickener? And then if we made it more efficient, you know, by a certain magnitude through implementing process control, how much difference would that make? That was what we looked at. So it was quite a simplistic assessment there.
And regarding the three options that you show of flow sheets, do you have anyone in particular that was best regarding operational cost or investment cost or footprint?
Yeah, so that's a great point. I mean, we I guess the variable, like this is just showing what the outputs were for the decisions. You know, the payback time on the optimized thickener was lowest, you know, like it's the shortest payback period, mainly just because it's you know, it's quite a small investment, but it's only able to provide a certain amount of water saving. So as we move to more sophisticated technologies like the filter press in particular, you know, it has a longer payback period. But when you look at the total cost of water for that facility, because of so there's different variables you would use to kind of compare them. Some of them, like they had different cost drivers, I suppose is the way to say it. In the case of the filter press, it's able to save such a significant amount of water and reduce the amount of tailings deposited to such a large extent that, you know, those savings are really where the economic business case comes from. Whereas in the case of the optimized thickener, you know, there's really no reason that they shouldn't have optimized thickeners if sites don't already do that, because the payback's so short. But as you move towards you know, filter presses, which are a larger capital cost and also have downtime associated with installation, etc., that has other economic drivers that need to be considered. So I hope that answers your question. But yeah, it depends on the technology and a lot of the variables that are going into your decision-making case.
All right, any other questions? So I think that was plenty.
Okay.
So let's
Thanks,
thank you again, Nadja, for this presentation. So next week we'll have Paul Hodjeskis and talking about the patterns and perspectives in mineral and mining systems. We'll talk about new technologies that can improve our understanding of mineral systems and support the development of integrated mining systems. So yeah, hope to see you all next week. Thank you.